number 3, which is flow in pipes. And this chapter is basically a continuation of the previous chapter, which was taught by Dr. Nasrul Hadi. And I, as your lecturer, Dr. Moin, is going to teach you on flow in pipes. And this chapter is basically a continuation of the Bernoulli equation, the continuity equation, and momentum equation. And some of the parts are going to be applied in this chapter, so it is quite important that you go back and have a refresher of chapter number 2. And in this chapter, the objectives are that first we are going to understand the concept of laminar flow and turbulent flow. Basically, how in a pipe the flow occurs, either it is smooth or it is very irregular or haphazard. So irregular and haphazard flow is called turbulent flow, and something along a streamline and a smoother flow is laminar. And how do we differentiate these flows? We are going to differentiate these flows by Reynolds number. So we are going to learn about the concepts of Reynolds number. Then once we have known about what is laminar, what is turbulent, and what is Reynolds, then we are going to understand that once water or any fluid which moves through a pipe, then what kind of losses it experiences. So we are going to understand about the minor losses and the major losses of flow in pipes. Then once we know about the losses, then we are going to determine what are the friction and what are the frictional effects, what kind of frictional factors are present, and how to determine them. And we determine them using the Moody chart or simplified Colebrook's equation. After learning about the friction factor, we are going to learn and calculate how to calculate minor losses, major losses, pressure losses, and head losses, and understand what is equivalent length. And then we are going to go through some difficult problems, for instance, which involve a pump, and then you've got a pipe, and then you've got a tank or something. So we are going to understand the whole system of piping network through solving piping systems using Bernoulli equation. So this is all about what you are going to learn in this chapter. The internal and external flow. It is important to know about the terms such as pipes and ducts and such as tubes. So it's important to learn how and in what terms they are used. So pipes is generally something where flow occurs in a circular cross section. So if the cross section is circular, then usually we refer to it as pipe. Usually in pipes, fluid or liquid flows, but sometimes larger diameter pipes are used for gas transport as well. When we talk about ducts, ducts are specially used in refrigeration, heating, and air conditioning, and usually the fluid is a gas. And tubes are basically smaller diameter pipes, and usually steam flow through it. So these terms will be used in this chapter, and it will be used descriptively, so that once we refer to pipe, it will be a circular pipe, or if we are going to refer to duct, it would be a rectangular duct. So let's move to fluid flow. Fluid flow can be classified in two kinds of flow. Number one is internal flow, and number two is external flow. So what is internal and what is external flow? If the fluid is flowing over a surface, then this is called external flow. And if a fluid is moving in a conduit or a pipe or a duct, then this is internal flow. So for instance, you've got a car, okay, this is your drawing of your toy car, etc., which you used to draw when you guys were kids. And if the flow is flowing over the body, okay, then this is external flow. And if you have got a pipe and water is moving inside and flowing, then this is called internal flow. This is a pipe. Sometimes you use air conditioning ducts as well. So the ducts is also an example wherein internal flow occurs. And there are various examples for internal flow, such as pipes. And then you've got blood flowing in a heart, okay. There is aorta, you've got left ventricle, right ventricle, and then the blood flows from lungs into the heart, etc. So there is a complete circulation system all over, which is being carried out by your small organism, small tissue, small organ called heart. Then you've got oil and gas industries, and you've got a huge piping network. You can see here you've got thousands of pipes, and these pipes, either air is flowing or steam is flowing, or sometimes cooling water is flowing, etc. Then there is drainage, etc. So there you've got different types of piping systems and networks available. Then you have got even more smaller systems, like a cooling system of a car or a radiator, which we will see in the next example. And air conditioning example is an example of a duct, DUCT. So this is all about flow in internal flow and external flow. Here are examples for internal flow. So here is an example of a heart flow, and the fluid is flowing inside the heart. There is one is oxygenated blood and one is deoxygenated blood. So here is an example of fluid flow in a pipe, and here you can see that you have got hot and cold water mixing up to get a different or intermediate temperature water. Example of internal external flow as well. So what is happening is that there is internal flow in pipes through the radiator, and then there is a stream of air which is being forced by a fan, okay, and this is external flow. So combination of external and internal flow helps us run our. So here is an example of a flow over an external body or an external cylinder, and it looks like initially the flow is laminar, but once the fluid moves across the body, then it becomes kind of a zigzag. So this could be a transition. So basically initially what happens is the fluid may flow laminar way, then there is a transition period, and then it could become turbulent. So how to determine whether the fluid is laminar, transitional or turbulent? It is based on this Reynolds number, which we are going to learn in this. Whenever you are going to be asked about laminar flow, you are going to say that laminar flow is characterized by smooth streamline, highly ordered motion, and usually it is shorter in length, and this normally appears in high viscous fluids such as oil, very thick glycerine, thick fluids such as honey. Likewise, the turbulent flow is characterized by rough streamlines, highly disordered motion, and most of the flows in reality such as lakes, sea, flowing rivers, exhaust, etc. are usually turbulent, and this is due to, as I said earlier, high momentum and high causing high friction. Whereas transition flow is basically a transition from laminar to turbulent, okay, and usually it is ignored in calculation because sometimes. So we can verify the existence of these laminar flow, transition flow and turbulent flow by injecting some dye. So if I've got a pipe and I'm going to inject some dye and ink or something inside, then I can visualize the flow. So this is what a British engineer, Osborne Reynolds, he did in 1880s. He did it over 100 years ago, and what he saw was the existence of these laminar, transitional and turbulence flow. So what happens is that when we put a dye in a pipe and where a fluid is flowing, then what happens is that we observe that the dye streak forms a straight line, okay. It is a straight and smooth line at very low velocities, and this is laminar flow. Sometimes we might see a little bit of fluctuations, but that's it becomes back to smoother streamline flow. So this is called laminar flow. And then there are some bursts which happen in transition flow. This is when the flow wants to transform to a more rapid movement, turbulent flow. Turbulent flow is basically characterized by rapid zigzags and disorderly flow, and it becomes fully disordered and zigzag, and this is turbulent flow. These zigzags and dispersion of the dye are indicative of fluctuations in the main flow and rapid mixing of fluid particles. So what's happened is that if you've got a pipe and initially it was moving streamline, then there was transitional, and then there was rapid inter movement. So what happens, the dye mixes with the water and becomes changes the color of the water. So this rapid movement is basically intermolecular mixing. So this intense mixing is basically turbulent flow as a result of rapid fluctuation, and it enhances the momentum transfer. It enhances momentum transfer between the fluid particles. So it enhances the momentum transfer between fluid particles, and what happens is that more of the water particles are basically going to strike and try to move to the walls, creating more friction. And when there is more friction, then what happens is that when I'm going to pump water, I've got a pump here, okay, then I need more power to overcome these frictional effects. So the friction factor reaches a maximum value when the flow is fully turbulent. Okay, so when at which values of Reynolds number are these flow changing? So basically for Reynolds number less than 2300 the flow is laminar, between 2300 and 4000 the flow is transitional, and larger than 4000 is turbulent flow. So what is this RE? So what the question is, what is a Reynolds number and why this number distinguishes these flow? So Reynolds number is denoted by RE, and this is equals to the ratio of inertial forces whole divided by the viscous forces. And the formula is average V average into diameter whole divided by viscosity kinematic, or if you want to convert it into dynamic viscosity, this comes out to be density V average diameter whole divided by nu. So here the rho is density, d is internal diameter of the pipe, okay, and this is the average velocity. Remember that we have got a pipe, okay, and when we have got motion, then the velocity profile looks like this because of no slip condition. Here the velocity is considered to be 0 because of considering the frictional effect. So the velocity profile looks like this. So what we do is basically we take the average. So we take the average V average. So the formula here is rho Vd over nu, and mu is kinematic. Once again, this is dynamic viscosity. This is kinematic one. So once again, it is a ratio of inertial forces whole divided by the viscous forces, rho Vd whole divided by mu. So these are some of the ranges for laminar, transition and turbulent, and we need to understand how these transitions and what are these Reynolds number 2300 etc. So first we need to understand that when laminar happens when we talk about Reynolds number, then laminar happens when the inertial forces are not dominant, only the viscous forces are dominant. That is why very thick and viscous fluids have laminar flow. Why? Because viscous forces are dominant. When the viscous forces are dominant, then the Reynolds number decreases. When the Reynolds number decreases or it is less than 2300, then we have laminar flow. So at small or moderate Reynolds number, however, the viscous forces are large enough to suppress the fluctuations which are caused by inertial forces. Okay, and what happens in turbulent flow? So in turbulent flow, the Reynolds number is high because the inertial forces, let's say forces inertia, are very high, and viscous forces due to viscous, are not high enough to suppress the inertial forces. So at large Reynolds number, the inertial forces also proportional to fluid density and velocity square. So these viscous forces cannot prevent random and fluctuations in the fluid. So these forces Fv, they cannot prevent the random fluctuations. That is why turbulent flow occurs. Now the critical point is that the Reynolds number at which the flow becomes turbulent is called critical Reynolds number, RCR. This is very important. Once again I will repeat, the Reynolds number at which the flow becomes turbulent is called critical Reynolds number. Okay, and you should know the Reynolds number RE has no units. It is dimensionless. So now that we know that Reynolds number RE is equals to rho V d whole divided by mu. Okay, so this is diameter, right, for a pipe, internal diameter. But what happens if we're going to see flow in rectangular or square shapes? Then what will happen? When we have rectangular or square shapes, then we use hydraulic diameter. Hydraulic diameter is denoted by dH, and this is equals to 4 times cross-sectional area whole divided by internal perimeter. So let's say that this rectangle has dimension A, height and the width is B. Then rectangle's hydraulic area is equals to 4 times the area. Area is A into B divided by perimeter. Perimeter is 2 times A plus B. This comes out to be 2AB whole divided by A plus B. This is hydraulic diameter for rectangle. If we talk about square, hydraulic diameter for square, then we have got here is A and here is A. So the area, 4 times area is 4A square divided by perimeter. Perimeter is 4A. So the hydraulic diameter comes out to be A. So remember that the Reynolds number depends on diameter or hydraulic diameter, and although it is not basically given, but usually the frictional effects also comes to place due to surface roughness, RA, or vibration also are the causes of fluctuations in Reynolds number. So we usually assume that the flow does not have surface roughness, and there are no pipe vibrations, and there are no fluctuations in the upstream flow. So otherwise, if you take into consideration these factors, then maybe the Reynolds number might fluctuate. Anyways, this was all about hydraulic diameter.